Hello, you're welcome back. All right, so here we are going to be looking at electric field. Okay, electric field. Now, what's electric field? Now, electric field is defined as a region in the space. Region in the space. Okay, where electric force. Where electric force is being experienced. Okay, and why is force being experienced in that region? Okay, is due to what? Is because of or due to the presence, due to the presence of a static charge, due to the presence of a charge. Okay, so we don't really see we don't see the force, but we know that in that region there's a force is being experienced. Okay, so that's what they call force field. A force field is not a contact force, but it's a region in the space where force is being experienced. So for electric field, it's a region in the space where electric force is experienced due to the presence of a charge. Okay, so that simply means that if I have a charge Q and that charge is located around this region, in this space, then you discover that this region we have this charge will create a field around this region, an electric field around this region. That is the reason why if I should bring another charge, let's say this charge is Q1, if I bring a second charge Q2 close to this region, what happened? This Q2 is going to experience a force. Why? Because there's a region where this Q1 have created a region where force is being experienced. All right, and that is why any charge, no matter the number of charge I bring around this region, those charges they are going to experience a force. All right. So now, though it's called a field, you cannot see the force, but the force is being experienced. Okay. So how do we actually represent the direction of the force experienced in an electric field? So we use what is known as electric line of force. Okay. Let me use a different color here. Electric line of force or electric field line is the same thing. Electric line of force. So since we can't see the force, but we can actually draw a line, that shows the direction of the force. So electric line of force is simply that imaginary line that we draw in an electric field. Imaginary line drawn in electric field. Okay, so that imaginary line actually shows the direction of the electric force on that region. Okay, so what that line does is that the line actually shows the direction of the force around the region. It's an imaginary line. For example, let's look at I'm going to give you a typical example. We are going to look at line for just isolated charges. Isolated charges are charges that isolated electric charges that are on their own. They are not close to any other charge. Okay, so I will start with isolated positive charge. Isolated positive charge. Okay, now I'm going to draw the line of force. So this is how the line of force is. The arrow always points outward. Okay, now one characteristic of electric line of force is that they don't cross each other. So this is for an isolated positive charge. take note that the arrow is always will point outward. Then isolated negative charge, okay, that is isolated, of course it's going to be the same, but this time around the arrow points inward. So for positive charge, arrow point outward, but for negative charge, arrow points inward. That's number one. Okay, let's look at for unlike charge. Of course, two unlike charges. That's a positive and a negative charge. Okay, let's see how that works. This positive and this negative. We know very well that there's going to be attraction. Okay, so the line will move from the positive to the negative. Please pardon me. So the line goes this way. It's curved. So of course the arrow will always, I will draw the arrow at the center. Why? Because the direction of the force, okay, is always from the positive to the negative, and the force is tangential, that is horizontal. So the direction of the force is pointing towards the negative. So please take note of that. Okay, so what if the charges we are dealing with are like charges? How do we draw their line of force? Okay, let's look at positive. A positive charge, and of course another positive charge. You know what happens when you bring two positive charges together, okay? There's gonna be repulsion. So the line will actually move away from each other, okay? But the arrow, don't forget the arrow is always pointing outward for a positive charge. Okay? Arrow is always pointing outward for a positive charge. Then, of course, the same thing goes with a negative charge. There's still going to be repulsion. Okay? So, arrow will, this time around, point inward. Arrow will point inward. So, I believe you draw that well. Okay, so I hope that is well understood. Electrical line of force. So it simply means that with this electric line of force, you can actually, okay, you can predict the strength of the field around that region. So a situation where you have more electric line of force, the number of line will tell you the strength. Okay, more lines means more strength of the electric field, and that tells you there's going to be more force experience that will be experienced around that region. Okay, so now that will lead us to the next subtopic, which is electric field intensity, a vector quantity. Okay, electric field intensity, the intensity of electric field, or the electric field strength, is the same thing. Okay, and of course we use the symbol E to represent that by symbol E. What's electric field intensity? Okay, now electric field intensity at any point in an electric field is defined as the force due to a unit charge in that region. The force experienced due to a unit charge. All right, force per unit charge. So electric field intensity is F all over Q, and of course the SI unit is going to be equal to SI unit of force is Newton and that of charge is coulombs. So the SI unit of electric field intensity is Newton per coulombs. All right, so this is one formula of electric field intensity. Now another way of expressing electric field intensity is, okay, by putting the value for electric force. Of course, you know very well that electric force from coulombs is KQ1. Now, since we are dealing with just as a unit charge, so it's gonna be both Q times Q. That gives me Q squared. Then all over distance apart. Okay. This is for this force. Then of course divide by the charge. So in this case now you know very well that Q will actually, okay, cancel Q squared to give me just Q. So electric field intensity can also be expressed as KQ squared. Please, not KQ squared, okay? KQ, all right? Then divided by R squared. So this is formula number 2. So it's either I use this or I use this, okay? All right, I hope that is well understood. Let's look at a typical example. Let's look at a situation where we have an electric field, okay, strength, okay, we have an electric field that's having the strength of 20 Newton per coulomb, okay, and we are being asked to evaluate the force on the charge of 2 microcoulombs. So in this case, the formula you're going to use is E is equal to F all over Q. So to get this force, you know what we do, have to cross multiply. So that means the force is going to be equal to the electric field intensity multiplied by the charge. Okay, so electric field intensity here is 20, then multiplied by the charge, which is 2 times 10 raised to the power minus 6. Okay, of course that gives 40 times 10 raised to the power of minus 6 Newton. Okay. All right, so now we are going to look at the principle of superposition. Okay, now this electric field is also a vector quantity, so it will still obey the principle of superposition. Principle of superposition of electric field intensity. Okay, now let's look at a typical example. Let's look at a situation where you have a point A in an electric field, and that point is 10 cm from a charge Q1, whose value is minus 2 microcoulombs, and it's also separated, okay, by the same distance from another charge Q2. Okay, let me use this point A. Okay, I have point B with a charge QB whose value is minus 2 microcoulombs. Let me use alphabet this time around. Then another, this point C, okay, with a charge QC whose value is let's say 1 microcoulombs, and the distance is still 10 cm. Okay, so and now you are being asked to evaluate the electric field intensity at point A. Now if you want to find the electric field intensity, The electric field intensity here is not just going to be due to the charge QB at point B. It's also going to be due to the charge at C, okay? Because charge at C, we're going to have an electric field around A, and the charge at B will still have electric field around A, okay? So the total electric field at A, EA, is going to be equal to the electric field, okay, at A due to the charge at B. So I'll call it AEB. Electric field at A due to the charge at B. So let me use AEB to represent that. That means this electric field here, I'll call it AEB. Okay. Then of course I have another electric field at A. This time around due to the charge at C, I'll call it AEC. Okay. So now that is going to give me the total electric field at A. So now let's evaluate it. So EA is going to be equal to, let's start with the very first one, EAB. Of course, we go by the formula. Okay, since we are being given distance, that's going to be K, okay, QB divided by, let me call it ROB, okay, ROB square. Then plus K QC divided by ROC square. Of course, that's the formula, the second formula of electric field I actually gave you. KQ all over R square. KQ all over R square, right? Okay, so now let's evaluate this. So EA now is going to be equal to, I can factorize, since K is common, I can factorize K out. I'll take K out and I'm going to have QB divided by RB square, then plus QC divided by RC square. Okay, so let's evaluate. So electric field at point A is going to be equal to 9 times 10 raised to the power 9, open brackets, charge at QB is minus, that's minus 2 microfarad, right? 10 raised to the power of minus 6 divided by the distance. The distance from A to B is 10 cm, and that's 0.1 square. Then plus QC is 1 microfarad divided by that distance. Okay, distance from C to A, 10 plus 10, that's 20. So I'm having 1 times 10 raised to the power of minus 6, then divided by 0.2 square. Okay, so let's evaluate. I work on the bracket. Bracket open. Okay, so what do we do exactly? So here I'm gonna have 2 divided by 0.01. That's gonna be minus 200 times 10 raised to the power minus 6. Then plus 1 divided by 0.04. Okay, 1 divided by 0.04, that's 25 times 10 raised to the power minus 6. Okay, so okay, I don't need to, my bracket is too long, I don't have denominator again, so let me shorten it. So 10 raised to the power minus 6, 10 raised to the power minus is also a common factor. I'll take it out again. So I'm having 9 times 10 raised to the power 9, then times 10 raised to the power minus 6, another common factor, bracket opened, minus 200 then plus 25. Okay, so that's minus 175. So that's what I have inside this bracket. So I'm having 9 times minus 175, then times 10 raised power 9 times 10 raised power minus 6. That's going to give me 10 raised power 3. Plus 9 minus 6, that's 3, right? Okay, so let's multiply 9 times 75. What do I have? 1575. I'm having minus 1575. Okay, then times 10 raised power 3. Okay, you can put that in standard form, moving 1, 2, 3. That's 1 point. I move the decimal point 3 times. 1, 2, 3. 1.575. So since I moved the decimal point, don't forget this is negative 3 times, so I have to add 3 to the power of 10. All right, so I have times 10 raised to the power of 6. So what's my SI unit of electric field? Don't forget it's Newton per coulomb. All right, so that is the principle of superposition of electric field. Okay, so I hope that is well understood. All right, we will actually continue in the next video. See you in the next video. Thank you very much.